Gentlemen, I get the sign. We are starting now official. I start with the greetings to the auditorium. First of all, thank you for joining all our roundtable. We start with the GaN session, and we have experts here. We will start, I will introduce them quick. It's Alex Lidow, CEO and co-founder of Efficient Power Conversion, Nigel Springett, Director of Springbüro in Germany, Larry Spaciani, Vice President Sales and Marketing at GaN Systems. We know each other also for a long, long time. Then we have Mike Wens, CEO of MinDCet, and Michael Zimmermann, R&D hardware engineer, automotive and energy solutions at Keysight Technology. That will start our first hour to review questions regarding our articles which had been published in the past quarter or past couple of months, and the auditorium can send us the questions in or have already sent questions in that we now can address to the speakers. And so I will straight go on and start. A question for MinDCet. Unleashing GaN with high performance gate driving. Why did you choose for such a complex gate driver? What's your position on monolithic integration of GaN? And that's addressed to MinDCet.
Okay. Thank you, Bodo, for posing this question, and thank you also for the person that's posed it. It's a valid question, and to be honest, I anticipated a bit on this question. So first of all, it is indeed, compared to other solutions, a quite, I wouldn't say complex, but a versatile gate driver. So there is a lot of functionality in there. But it is there for a reason. It is not there just to make it better or different than others. It's there for a reason. And the reason is namely reliability and speed. So all of us know that GaN components can be used to increase the switching speed. Now, if you do that, and even if you have very well control over your board parasitics and your system parasitics, you will inevitably have some overshoot, some undershoot, and some parasitic ringing because of inductances that are there on the boards, on the drain, on the source, and on the gate. And even if you do the best job in layouts and module design, you will still have it. And even if it is, let's say, in the nano-Henry range where you can easily achieve, then you are switching still at high DVDT, and you will inevitably have some ringing. Now, this ringing, also related to the high switching speeds, will introduce a number of potential issues. And one of those issues is what we call gate overcharging. So in a bootstrapped circuit, when and on a half bridge, so when your low side is on, you will see a negative spike on the source inductance, and this will create this negative voltage on top of your bootstrap voltage to create an over voltage on your bootstrap capacitor. And this can be a problem for GaN because GaN is, I wouldn't say very sensitive, but it is more, the gate voltage needs to be more constrained. You don't have so much headroom as you do with MOSFETs. So if you need, for instance, 4 volt on the gate or 6 volt on the gate, you don't want it to be 7 or 8 volt because this will maybe not destroy the device in short term, but could create a reliability issue. So one of our features is a floating regulator, to come to my point, or two floating regulators, in fact, for the high side and for the low side. And they will make sure that the gate voltage is what it should be or what the user wants it to be. Because it is regulated, and this issue is gone then. You don't have gate overcharging anymore, and as a consequence you gained a higher reliability. So this is one of the things that makes the gate driver more complex than other solutions. Another solution, for instance, the charge pump. There is bootstrap diodes, but there is also a charge pump on the chip that enables you to have 100% duty cycle of the high side, or very high duty cycles that would not be achievable with bootstrap diodes. This is, of course, a function. This will depend on your application, whether or not it is needed. And I fully understand and agree that certain applications have no need for this functionality. So that is, of course, a trade-off that needs to be made by the users. So in general, I would say our gate driver is not a one-fit-all solution. It is a solution where the user wants the combined speed of GaN with the reliability that it can provide, and in some cases additional functionality such as charge pumps. Now, in relation to monolithic integration, we are very much active on that as a side comment. So MinDCet is involved in a number of projects, including research projects where we do monolithic integration of GaN ICs. And this is a very promising technology, in fact, and a very promising way of getting even better performance out of GaN, because now you are able to completely kill the gate inductance loop and put your gate driver on the same physical chip as your switching devices. And this is very nice. However, today, with this monolithic technology still in early days, it is, for instance, not possible to have complementary devices like you do in CMOS. In other words, the complexity that you can make on such a monolithic GaN chip is rather limited. We are now working and have successfully implemented also a high voltage level shifter that can work up to 200 volt. I will present this at the APEC conference later this year. So it is possible with some imagination to make, let's say, components that take over the function of a discrete gate driver, but you can never at the moment take over all these functions. So although it is a nice solution for the future, today it is still rather limited in the things you can do. And the main advantage today, I would say, is the fact that you indeed can put your gate driver very, very close to the physical gate of your switching device. Also there, I need to say, it is not a solution that brings all the goods, or it's not a miracle, let's say. So for instance, your bootstrap capacitor will still be off chip, and the connection of this bootstrap capacitor to the on-chip gate driver on your monolithic GaN die still has some inductance, and this inductance is in fact in the gate loop. So still you have some worries of parasitics. So you need to think about these things and keep in mind that all of these wonderful solutions, they are still not miracle solutions. So you will still have certain issues, although clearly the issues improve, or they reduce, in other words, and your overall performance can improve. That is true.
Thank you, Mike. I see Alex, you gave me a hand. Do you want to add some comments?
Sure. I'd just like to say that for a year we've had a monolithic, power stage out on the marketplace, the EPC 2152, which is 80 volt input, and it has the power FETs, it has the over voltage protection, it has the bootstrap circuit, it has input logic. The limitations of not having a complementary device are real. But the advantages of integrating all the drive function and level shifting onto a monolithic chip with the power devices, it gives a huge benefit. You eliminate power loop inductance, you eliminate common source inductance, and you eliminate gate inductance. So it's a very, very big advantage to do that. And I frankly, I don't share Mike's concerns about limitations of integration in GaN. I think that there are many ways to go to high density logic, and we're certainly working in that direction. We also recently introduced, and it was in Bodo as well, the driver plus the FET for high-speed LiDAR applications. And that eliminates the gate loop inductance and gives you picosecond rise in fault times, which requires low picohenries kinds of inductances in your circuit.
Okay, thank you, Alex. That leads me to the question to you. Question for EPC, ultra-fast switching with integrated driver for indirect time of flight laser drivers. I think you had mostly mentioned that and answered that, since the question was, since the LiDAR application is switching currents at plus minus 10 amp per nanosecond, how is ground bound solved for controlling the EPC 21601 power switch? Is level shifting integrated, or is it an external level shifter recommended? That question came in.
So the laser driver, the 21601, is a low side driver. So there is no level shift involved, and ground bounds you take care of by having a different logic ground and a different power ground. I would like to point out that in many of these cases, we're seeing 100 amp per nanosecond rise DIDTs and 200-300 volts per nanosecond DVDTs. So in general, you have to be concerned about DVDT, but all GaN devices that come from EPC were designed with Miller ratios below 1. So there's no way to false trigger a device through very high DVDT, which I get that question very often. So for a low side device, there is no level shifting issue. The ground bounce is taken care of with separate grounds for the power and for the logic, and there are no issues of DVDT coupling.
Thank you, Alex. I have a couple more questions regarding subjects that related to your IC. The question is, what I have here is, the new time of flight IC, the FET and gate driver combo looks very impressive. How about thermal? It seems like it may heat up. Does it need a heat sink?
It's a very good question. In all LiDAR applications, the laser is the hottest thing on the board. So the laser turns out to be the thermal constraint, and our devices really never heat up. There's no way we can put enough energy through our device to get our device hot before the laser is overheating. So thermal management is not an issue with GaN.
Okay. Let me just see. I have missed one question on that note here. Thank you, Alex, for that. This question is addressed for measurement, and that's for Keysight. And question for GaN systems, advantage of 100 volt GaN in 48 volt applications. You demonstrate that maximum current capability decreased with switching frequency. Do you see a trade-off between switching frequency and system efficiency, or is faster better?
Okay, that was to me, I think.
Yeah.
Okay, let me address that. Thank you. Yeah, of course, switching frequency and efficiency are a trade-off, just like in silicon. I think the point of the article is that optimizing thermal and switching frequency, and of course RDS on, is all all the same trade-offs engineers have been making for ages and ages with regards to switching circuits. The point in the article about optimizing 48-volt systems is you have to consider thermals. When you're switching at very high frequency, of course, GaN has significantly lower losses than silicon, but it's not infinitely low. So you have to manage thermals as well. Part of our packaging technology and our topside cooling helps customers maximize the amount of heat they can get out of our devices, which allows them to go to higher frequencies, shrink the overall circuit, and still manage the thermals. So it's really a trade-off of frequency, RDS on, and cooling in a 48-volt system.
Thank you. Okay. Thank you, Larry.
Thank you.
So in the meantime, I can look to a question which is also addressed to Alex. The question is, with sharp high frequency square waves, it's hard to avoid radiation emission at higher order harmonics. How do you mitigate against this? Do you have design guides to minimize radiated emission?
Yeah, EMI is a very frequent question because of the fast switching speed of GaN devices. We wrote a paper on this. I don't think it was published in Bodo, but it is on our website, and there's also a video explaining this. So first of all, fast rise and fall times in and of themselves don't generate more EMI energy. It's the same energy. It just shifted out in frequency. So it takes it out to a frequency where it's actually less expensive to filter it. But the best way to avoid EMI is to not generate it. And for that, the EPC's chip scale packages, which have no internal inductance, allow you to make circuits that have very low parasitic overall inductance, especially if you use the optimal layout that has flux cancellation, which we have also on our website to show you how to do that. When you do that, your overshoot goes way down, and overshoot is a major contributor to EMI. And then the other factor in EMI that most people forget about is when you use a silicon device in a hard switching application, the reverse diode has a recovery time, and that is a major source of EMI, and GaN doesn't have that. So you do have to be careful. It's about stray inductance. It's about reducing overshoot. But if you use a GaN device from us with no package inductance, you can get a very, very clean waveform which has the lowest EMI. But you certainly have to be careful in your designs when you're at high speeds.
Thank you, Alex. Now the Keysight question showed up, had sneaked down in my pile of paper. The question is, the current probe is identified as a problem in previous measurement setups due to the introduction of additional inductance in a loop where a high IDT is present. It is stated that it has been solved. Can you elaborate on this solution?
Yes, so first, thanks of all for your question. Basically, the issue with the current sensing technologies which were available is it's either a large solution, for example, if you have a Pearson probe with the according bandwidth for example, 200 megahertz or more than that, your Pearson probe has quite a certain size, and you have to adapt your circuit quite a lot to fit it on your board. The most common shunts which are used to do this job are basically radial shunts, which have a BNC connector on it, so current travels up and down. So the the effective inductance is really low, but you still have the the insertion inductance in your power loop. So I cannot speak too much about the solution that we've created. It's basically it follows the principle which is also used in the common radial shunts, but the overall by just decreasing the dimensions and decreasing your parasitics, you can get it to much lower insertion inductance compared to the commercially available products.
Thank you, Michael. I got the question printed. In the meantime, I will take one which I have here. That question was also addressed to EPC. What's an accurate method to sense the current making it to the laser?
Yeah, so this is I think a follow-on to the current sensing question, and it's you know, clearly everybody wants to measure current, and it's really hard to do when there's enormously high IDT. So first of all, we have an application note on it, AN 027 on our website. But what we do is we on the low side, we use ground reference shunt in series with the low side of the main discharge capacitor on our device. And the shunt uses multiple parallel resistors, which and the resistive elements are facing the PCB to minimize inductance. And you know, we get below 100 picohenries with this, actually closer to 50. But again, that's still enough. If you're doing 100 amps per nanosecond, 50 picohenries is 5 volts. Okay, so that's still too much. So we have to use a passive compensation network. As I said, we have details of the schematics, and they're all available on the website. So if you write down, you know, app note AN 027, you can find that there on our website.
Thank you, Alex. That question is a very generic one. What is experts' vision about vertical GaN device development in terms of time, horizon, potential, and cost competitiveness? So I hope that question came well out.
Did I take a shot at that, Bodo?
Yeah.
Okay, so you know, thanks for the question,
Larry.
Vertical GaN is possible. There are people experimenting with it. GaN, you know, part of the benefits of and the popularity of GaN today is because GaN is on a silicon substrate. It's highly manufacturable. It's cost effective to the point of being, you know, equal to or below MOSFETs. All the processing in the fab is done on materials and machines that are used to doing, you know, 6 or 8 inch wafers in the CMOS technology. So GaN on silicon is lateral, and it's scalable, and it's high volume producible. Vertical GaN is possible. Last I heard, it comes on either 3 inch or maybe 4 inch wafers maximum. It's extremely expensive for a wafer. And the predominant market hoping for vertical GaN is, at least from the one I've heard, is the automotive market, where they're hoping to, you know, maximize size and the efficiency, and even get 1200 volts. So while it's possible, I don't see any path to having it commercially successful. And the cost and rarity of a pure GaN vertical wafer is really going to prevent that from happening. That's the opinion we have at GaN Systems.
Okay, thank you, Larry.
Bodo, can I
Alex,
just
yeah. Or Nigel?
Yeah, and one of the interesting things we noticed, especially I went through the process with vertical silicon carbide, is that especially for GaN, for power components, getting the heat out is one of the key issues. And we've experienced that even if you manage to get the chip very small, then you've still got to get the heat out of the chip. And usually there's some form of thermal interface material, which means you've got a very high power density in a small area. And so vertical GaN, although it might make the chip smaller, it doesn't necessarily make the solution smaller or cheaper.
Exactly. That's a good comment. I remember that when I worked with IGBTs and module solutions, some people said they preferred discrete IGBTs to spread the heat better in their applications. These are memories 25 years back.
Yeah, we saw the same thing with silicon carbide. We at SemiSouth in those days, we had very, very small chips with a lot of power, and the heat sinking was a disaster. It was really difficult. And of course, the more layers you have, then you've then got to get the heat through the various layers, so make the thermal resistance in the chip bigger as well. I don't think it's going to be for a long time a big advantage. And of course, the advantage, as Larry said, of the lateral is you just have a very simple process, very few processing steps, which makes GaN it's going to be very, very competitive in the near future.
Just to add a couple of things on that, vertical GaN, GaN is less thermally conductive than silicon carbide, so the heat problem becomes worse. And there's no improvement in electron mobility compared to silicon carbide. So I don't see the advantage of vertical GaN over silicon carbide. Now, lateral GaN at lower voltages has lots of advantages, and that's what EPC is doing. And a counterintuitive thing for everybody is that when we put two power GaN devices together monolithically in a monolithic half bridge, they actually heat sink each other, and it actually increases the thermal density. And I did not predict that. It was just a weird thing. So if you look at the efficiency of two monolithic, a monolithic half bridge, it is more efficient than spread two discrete devices of the same on resistance. And we've documented that time and time again. It's a magnificent thing about GaN and integration of power devices.
Is this when the duty cycles are very different, or is this when the duty cycles are similar?
You raise a good point. It's when the duty cycles are different, and then you tend to have different thermal differences between the two chips, no matter what the on resistance is. So it's exactly right. So on high V in V out ratio buck converters, that's where it's most pronounced. But even so, when you marry two devices on a chip, two power devices, you do eliminate the power loop inductance. And that also has a significant impact on the overshoot ringing and therefore thermal properties.
Thank you, Alex. I have another question, which also to EPC. Have these devices been used or tried in aviation applications? That's to the GaN devices.
So the answer to aviation, if you include space, the answer is yes. We have tens of thousands of devices circling the Earth, listening to us speak right now, and many companies designing with them.
Okay. I have a question also regarding this, where I did not have a clue to the shorten. I am using ITOF for inside the passenger compartment and short range exterior sensing for automobiles. Is there a plan to qualify the laser driver ICs to AEC Q100?
Yes, And it's a fantastic application if people don't know about it. You know, we see all these, you know, cars with level 2, level 3 automation coming out, but the problem is that drivers are falling asleep because there's not enough to do. So there's a booming business in creating driver alertness systems. And ITOF, or indirect time of flight measurement, which is what that little IC that we just came out with was designed for, is one of the primary applications is this driver alertness system, where now your car is watching you, and if your eyes stray from the road, it's gonna shut you down in automation. And yeah, Q100 is in the plans for later this year.
Thank you, Alex. We are just checking for incoming questions.
Do you mind if I comment on something that was earlier said, Bodo?
Larry, come in.
Yeah, thank you. I want to agree strongly with Alex on EMI. You know, throughout the history of our relationship with customers, probably two things have scared them the most. One of them is EMI, and as Alex said, there is higher frequency EMI. Because of the higher switching speeds, but it's not more energy, as he said, and it's easier and cheaper to filter. A lot of customers just assume that it's either near impossible or very difficult to filter for EMI. Without going into the technical reasons, I just want to point out an obvious situation. At last I counted, there are 130 low-cost, consumer-grade PC and phone adapters on the market from companies all over the world, using extremely low-cost manufacturing, using single-layer PC boards, using discrete parts, and passing both conducted to EMI and radiated EMI with -6 dB margin. So my point on EMI is it's actually quite easy, and it's counterintuitive. Most of the industry believes that higher speed means more difficult EMI. It's exactly the opposite, and the proof is in low-cost consumer electronics easily passing EMI specs. And then the second thing I'd like to comment is on automotive quality. As Alex said, his products are going into automotive quality for LiDAR. We have not only passed automotive quality in the industry for GaN. Most automotive customers just assume that the reliability of GaN is lower than silicon. Frankly, it's just not true, and we've been able to prove it. We've been able to achieve the fit rates of silicon, reliability, and the mission profiles, and it's there and it's ready. And I think customers that are afraid of reliability, you know, just talk to us as a collective industry. Just talk to us. We have the data to prove it. And it's ready, and it's already in automotive systems. Thank you.
Thank you, Larry. That seems to me the current automotive industry, the established one, is like the steam locomotive manufacturing society in the past. They had a hard time to make it, and they did not survive into electric and diesel. So I think that's the life. I remember that bringing in IGTs into motor control had a high resistance when I did that a quarter of a century ago. So my next question, which came up to my desk, is: can panelists talk about the price erosion in comparison with silicon? I learned as an engineer the most important physical dimension is price. If the price is not given, the application will not survive. But let me get your inputs.
Well, as the price driver, I guess I'm gonna weigh in here. you know, at the 100 volt and 80 volt level and 200 volt level, our GaN devices in volume are priced at or below MOSFETs. And have been for a couple of years. So I think that the price overhang issue is one that silicon people are talking about, but it's not real anymore. GaN devices are so much smaller than silicon that it's that the cost is now for you know 100 volt, 200 volt, and I don't know anything about beyond that because we don't make it beyond that. It's a lower cost of silicon. So that's one thing. Now, the minute you get into integration, the equation becomes even more severe when if you're in the silicon business. So, for example, that recent laser driver, the entire IC is priced less than the simple GaN driver that was there before, that was a silicon chip. So you can now get an entire IC that not just has the little driver function, but also has the power FET for less money than you just had the driver. So you know, silicon's just in the rear view mirror, and it's getting farther away.
Thank you, Alex. The next question addressed to all of you. What about gallium oxide? Niche applications for it. Timeline to commercializations.
You know, I'll speak for GaN Systems. It's not on our radar right now. GaN on silicon, you know, we're concentrating on high volume production. We've already ramped. I think others in this panel are in the same situation. There's no value that we see in gallium oxide in mainstream electronics, so we're not looking at it. I don't know if anyone else in the panel is.
Not at EPC, that's for sure.
Okay, gentlemen.
Mike, how about you? Are you looking at that at all?
No. And by the way, we're not really technology guys, so we just design the circuits. But as far as I'm aware, we're no, there's no interest in that.
Bodo, can I just, I'd like to come back to this EMI issue a bit. This has been an eye-opener for me from you, Alex, and from you, Larry, that of course the higher switching speeds are no more energy than lower switching speeds. And I just, as you were talking, I was thinking about this and thinking it's actually quite obvious, isn't it? Because EMI is caused by capacitances which you're charging and discharging and putting their energy somewhere where you don't want it. And of course the capacitances and the voltages they're being charged through, they're independent of the frequency you're switching or the speed you're switching at.
Right.
So thanks so much for this eye opener. It's sort of been useful.
There's so many dimensions to it, Nigel, and it's really a fascinating subject. There is a caveat to that, though. The faster rise in full time means that the slope of the EMI, which goes down at 40 dB per decade, continues longer at 40 dB per decade. And the minute you hit the node that's the inverse of the switching speed, so if it's 1 nanosecond, that'd be a gigahertz, then it starts going down at a faster rate, I think about 49 dB per decade. So there is a gentler slope down the faster your switching speed, but that is not such a big amount of energy. It's the overshoot and the reverse diode in a MOSFET that cause all sorts of problems. Also, when you think about it, if you have a circuit that big, that's your antenna radiating EMI. And if with GaN it goes to this big, then your antenna's also gone down. So the radiating EMI just naturally goes way down. So EMI has been a big question mark with simple answers.
Exactly.
Because you had GaN Systems managed to do a lot of this with the 600 volt range with the new packages and these extremely low inductance packages. And of course, you can get very compact half bridges and the way you've been doing it with the lower voltage, Alex. And,
right.
And I guess the other thing is that the 600 volts aren't switching so much faster than CoolMOS. I remember seeing 10 years ago, we were seeing over 10,000 volts per microsecond with CoreMOS when it turns off. And of course, GaN is just a lot smoother. It's a lot more gentle. We don't have the kicks and the capacitance and everything, which make life just generally better.
That's a good point, Nigel. It's I think I remember studying this with you years ago. Was in our GaN at the 650 volt GaN, the switching on and switching off DVDT tends to be more linear from 0 to full voltage. If you look carefully at a MOSFET switching waveform, it may appear slower during most of the ramp, but then as it approaches the top or the bottom of the ramp, it tends to speed up quite a bit. So you end up with higher ringing and higher energy there. And it's harder to deal with. And I'll agree with Alex, and it always, in any silicon, even silicon carbide solution, it really comes down to the QRR of the worst device in the system that rings like hell and has a lot of energy and causes EMI.
Also, you know, in resonant circuits, the MOSFET has a very nonlinear output capacitance compared to GaN, which is, you know, much more linear for output capacitance. So it tends to make resonant circuits more pure, and you don't have as much noise on them either.
Agreed.
Thank you, gentlemen. The next question came up to my desk. Do Egan FETs have truly no QRR and thus no forward and reverse recovery times?
Truly zero QRR. There is no minority carrier in our Egan FET, and the reverse recovery comes from minority carriers in silicon devices in a PN junction. There is a reverse conduction path, but that's because the FET automatically turns itself on in the reverse direction, but it's a conduction path of the FET, so it's instantaneous. So you do not have to deal with the reverse recovery time of a diode.
Thank you, Alex. The next question came into my desk. Building power supplies also requires control ICs, not only switching devices. Do you see the market being prepared for high switching frequencies, also with respect to control ICs?
Absolutely. I mean, the semiconductor companies across the board are taking well-known architectures, Boost PFC, Totem Pole PFC, LLC, phase shift full bridge, and they're taking all of those technologies and, on average, I would say doubling the frequency of the controllers, or even tripling. I think I'll speak for high voltage. I'll let Alex speak for low voltage. In the higher voltage AC to DC world, the controller companies have responded well, so that now the major, I'd say, limitation on the circuits tends to ride on the magnetics. So, you know, in the earlier days, the controllers didn't bother to go past 100 or 200 kilohertz because there was no reason to, because the silicon MOSFETs couldn't handle it. Now, a lot of controllers maximize at 700, 800, 900 kilohertz, megahertz, and then it becomes really a magnetic limitation. So a lot of the magnetic companies are now responding, but the controller companies have responded quite well.
Yeah, I think that one thing that helped was the fact that we were already moving towards digital control in power conversion. So there were a lot of digital controllers out there. So, you know, we now see a real wealth of controllers on semiconductor, microchip, ST, TI. So there's a bunch of digital controllers out there that really make life so much easier for the user once you get it programmed up, and is ideal for multi-megahertz switching frequencies in GaN.
You know, Nigel represents more of a user in this group. What do you think, Nigel?
I see in GaN two worlds, to be honest. I see the low voltage world where things are really changing. There are significant differences to silicon technology. The 650 volt world it's interesting. Most of the totem, I haven't seen any totem pole PFC topologies significantly above 150 kilohertz. Most of them are going for efficiency and still running around the 65 kilohertz area. I expect that we'll probably see some new generation GaN devices coming out with the higher voltage with lower capacitance, where then the higher switching frequencies don't hurt the efficiencies too much. But currently, I don't see in the high voltage area so much difference. I think we might see it in different topologies, phase shift, where the magnetics aren't the key issue as well, where you've got soft switching and you can use the magnetics better. So one of the issues we have, as you said, Larry, is the magnetics. We're still stuck with core losses and we're stuck with wiring losses. And so if we want to push the frequency up, we either have to use topologies where the core has a DC bias so we can store the energy in the core. But these topologies tend to currently be hard switched. And then we don't have the big advantage, such a big advantage. So I'm not too sure about by high voltage stuff where we're going to go yet. So I haven't seen the 10 years ago there was GaN on silicon carbide, and this was awesomely fast. It was so fast we couldn't use it. But I haven't seen this massive change in frequencies with the modern GaN parts so far.
One comment on PFC we published in Bodo about a year ago, I think. I don't remember the exact issue. It's a cross between switching frequency and power density. Now, if you look at the server industry and the 5G industry specifically in high voltage power supplies, power density is the dominating factor. Especially 5G is a great example. They're trying to get 10 times more power in the same infrastructure. So they have to get much, much smaller power supplies with much higher efficiency. So our analysis, and we've proved this with some customers, is power factor around 200 to 220 kilohertz is the ideal point where you can get a higher frequency. With GaN, the losses are significantly lower, so it's not an impact on efficiency. And the trade-off being, the EMI spectrum, because the reason people switch at 60 kilohertz is to stay below their second harmonic, below 150. Now, once you overcome that, it turns out that switching at about 200 kilohertz, it allows you to actually design a smaller EMI filter. It's not intuitive, but I think the customers that have figured it out have learned that you can achieve great power density by doing power factor around 200 kilohertz. After that, the efficiency does start to suffer. So if you're trying to build titanium class, it's harder. So there's a sweet spot, and I'll refer everyone to Bodo's magazine to read the article.
I would like to give a shout out here. Something that we haven't really brought out, but it touches on what Larry was saying, and that is, power density. One of the key things in power density is, of course, thermal management. And there has been huge progress in thermal interface materials. It used to be, as recently as 3 years ago, that like 3.6 degrees C, 3.6 watts per meter, degrees C per meter Kelvin. Is it right? No, watts per meter Kelvin, was the norm for thermal interface material. And from companies like T Global now, we're able to buy 17. And just to give you an idea, that more than doubles the power density of a system. And it has nothing to do with the on resistance reduction. It just has to do with better thermal interface material. So, magnetics used to be a barrier. You couldn't get much above a megahertz at lower voltages. Now, 2-3 megahertz is practical. And thermal interface materials are allowing GaN devices, which are like 5 to 10 times smaller than silicon, to get 5 or 10 times more thermally efficient. So it's really fantastic opening that's occurring in so many different areas.
That's really interesting, because this really takes us back to the point that having the higher density components, unless you can get the heat out of them, isn't going to help. And especially hard switching applications, then the switching losses become the key heat source, and that this stops you going to higher frequency.
advantage of GaN is you don't generate as much heat in the first place.
Yeah, but if it's so much smaller, you generate not as much heat, but in a smaller space. So you got to be able to still take out, watts per square centimeter. It goes up, and these new materials, and it's watts per meter Kelvin is the metric there. It's just fantastic.
And Alex, I don't know these. Are these then soft or are they very hard?
There's thermal interface materials. It comes in gel. It comes in pads, we write lots of papers on this sort of stuff on our website. But you can get a 4 square millimeter device. You can get to 4 degrees C per watt total system thermal resistance. And it used to be 4 degrees C per watt. Thermal resistance was something that was like 20 square millimeters that it took to do that. Now you can get that down into 4.
It's really impressive, yeah.
Gentlemen, thank you very much